Welcome to part 6, the final part of the further mathematical induction topic. We are going to be looking at proofs involving inequalities and graphs. Now for this video, I'd like to actually start off with a problem. Prove that 1 plus 1 on root 2 plus 1 on root 3 and so on all the way to 1 over the square root of 48. Prove that that sum is greater than 12. So I'd encourage you to pause now and have a go at this problem. Think about how you might attack it. Give yourself 10-15 minutes, and even if you get stuck, just list a few different methods that maybe could be used to prove this. How did you go? Pretty tricky, right? Well, before we talk about how to do this problem, let's get into the main part of our lesson. So most proofs we've seen so far have been algebraic, but sometimes results can be proved using a geometric or a graphical approach. And so with inequalities in particular, often they can be difficult to solve algebraically, but are a bit more straightforward if we look at the graph. So take this question for example. Solve x squared minus 1 greater than the absolute value of 2x plus 2. Now both these functions on the left and the right hand side are relatively easy functions for us to sketch. So if we sketch both of these, then to solve the inequality we just need to find where this function x squared minus 1 is greater than this function on our graph. So let's do a quick sketch first, and we'll start with our parabola y equals x squared minus 1, which I'll do in green. So standard parabola y equals x squared, move down 1. So we've got a y-intercept of negative 1, and it's going to cut through the x-axis at 1 and minus 1. Okay, and we'll label the points. Okay, now the absolute value of 2x plus 2, which we'll do in blue. Now remember, absolute value graphs, in this case it's a linear function. So if we think about that linear function first, gradient of 2, y-intercept of 2. So we're cutting through at 2, and if it has a gradient of 2, that means rise 2, run 1. It's also going to cut through minus 1. So let's draw a straight line that goes through those points. Okay, straight enough, right? And that was 2. So in terms of points of intersection, we can see one here quite clearly at x equals negative 1, y equals 0, and there's another one up here somewhere. So it would be a good idea if we actually find these points of intersection. And so we can do that by focusing on equality rather than the greater than symbol. So let's set x squared minus 1 equal to the absolute value of 2x plus 2. Now what do we have to do when we're solving equations involving absolute values? Well, we need to consider the positive case, but we also need to consider the negative case. since the negative version of this just turns into a positive anyway due to the absolute value signs. So let's solve our first inequality on the left. Sorry, our first equation on the left. Moving the 2x over and also subtracting 2 from both sides, we get the following. Factorising, we can see that we have x minus 3 and x plus 1. So that gives us x values of negative 1 when we set this equal to 0 and 3 when we set this equal to 0. Over on the right hand side, we get x squared plus 2x when we move this, and we're also going to plus 2 to both sides, and this is a perfect square, so we can see that x equals negative 1, which we already got over here. So going back to our graph, and I should note, silly me, that this is just y equals 2x plus 2, whereas we want the absolute value. So anything that's below the x-axis that's negative, we need to flip that up. So that's better there. And this bit here is not really part of our graph, but I'll leave it there anyway. Okay, but regardless, we can see that from negative 1 and any x value to the left, our x squared minus 1 parabola is greater than our absolute value of 2x plus 2. And over here on the right, we just worked out that this is x equals 3. Okay, this point here. And so as soon as we go past 3, then once again, this is where we have our parabola greater than our absolute value function. So finalising our answer, we can say that x must be less than negative 1, or x must be greater than 3. And there we have it. Alright, let's move on to some proofs involving areas. Let's just review some general integration concepts. We know that to find the area under a curve, such as this one here, we can find the definite integral between a and b of our function of x. This definite integral will give us the area under the curve. But before we got to this stage, we learnt about approximating areas using rectangles. In the case of inner rectangles, like we see here, we notice that there is error. So the area of the rectangles is less than the true area under the curve. And in the same way of thinking, we could use outer rectangles, where there is still error, but we can see now that the sum of the rectangles is greater than the area under the curve. Let's now use these observations to help us with another example. Considering the areas of the n rectangles, each of width 1 on n, under the curve y equals root 1 minus x squared as shown, show that the sum an of the areas of the rectangles is given by this expression. Alright, so there's a bit to unpack, so before we jump into part A, let's just observe our diagram and understand what's going on. So this function, square root of 1 minus x squared, this is a circle function. right? It's the positive half of a circle, radius 1. So it's a semicircle, but we are just focusing on this quadrant. So we're only going from 0 to 1 here. Okay, and underneath this circle function, or this quadrant function, we have lots of rectangles. We have n of them, right? N rectangles. And because they've all been evenly divided amongst this length of 1, the width of each of them is 1 on n. Right, so if there was 10 rectangles, they would have 1/10 as their width. If there was 100 rectangles, it would be 1/100th. We need to show that the sum of all these rectangles is given by this expression. What we need to do is just focus on one rectangle at a time and see if we can manipulate that expression, and then we can add all of the areas together. So if we focus on this first rectangle here, what is its width? Well, 1 on n. And what is its height? Well, its height is going to be the value we get when we substitute in this x value of 1 on n into the equation of the curve. Likewise, when we focus on this second rectangle, we would get its height by substituting in 2 over n into the function. Now we can see each of the x values that we're substituting in is of the form x over n. So why don't we look at a general rectangle first of all? So some general rectangle would have a width of 1 on n, and its height would be the function 1 minus x squared, where we are substituting in the x value, x on n. Right, so we're looking at the area for some general x value, or rather some general x on n value, because just going back here we notice that everything is of the form x over n, some x value over n. So what would our area be? Well, it would be the width, 1 on n, multiplied by the height, which is 1 minus, I might start tidying this up a little bit, x squared on n squared. Because we notice that in what we're trying to prove, everything under the square root, there's no fraction there. So we want to get rid of this fraction. So let's keep messing around with this expression. How could we get rid of the fraction? Well, first of all, it might be a good idea to combine. So if we were to combine these two into 1, we want a common denominator of n squared. So we'll turn our number 1 into n squared on n squared. And that way, with our common denominator, we can combine the two fractions. Now notice what we've got here. We've got n squared minus some x value squared. And look at the form of what we see on the right hand side here. This is 1 squared, so even though they've just written 1, this is 1 squared. This is 2 squared, all the way up to n minus 1 squared, which is our last value. I mean, just going back to the diagram, we could say that the last rectangle is here at our 1 value, but then that just gives us a rectangle of no height. So for all intents and purposes, this is our last rectangle, n minus 1 on n. But notice what we're after, like I said, no fraction. So what are we going to do with this n squared? Well, if we take it out of the square root function, it just becomes 1 on n, right? The square root of 1 on n squared is just 1 on n. And then we are just left with n squared minus x squared under the square root sign. And this is good, right? Because notice what we have here, and what we're trying to show is a 1 on n squared value out the front. So if we apply what we've seen here with some general rectangle to our different values, we see that no matter what x is, so if we come back here and we say, let's look at the area of 1 on n, right? That 1 on n rectangle. And so we replace x with 1. We're just going to end up with 1 on n squared outside of n squared minus 1 squared. And if we look at the next rectangle, where we have 2 on n as our x value, well, same thing. We're just going to end up with 1 on n squared right out the front, then our square root sign, n squared minus whatever our x value is, which now is 2 squared. And so on. This is going to continue all the way until we get to that last value, which was n minus 1 on n. And so this was the last one that we saw in that big sum. When we look back up at the original question here. So let's sum all our rectangles together. Our first rectangle and our second rectangle all the way through to our last rectangle. And when we're doing this, we notice that because they all have a 1 on n squared that is common, we can drag that out the front. We can factorize. And so when we drag that out the front, this 1 on n squared, then we are left with all of these radicals, like so. And that's part A done. Alright, part B. Hence show that the limit as n approaches infinity of this function, this 1 on n squared, etc., equals pi on 4. Now remember, this function here is just the sum of our n rectangles. And so what does it mean for n to approach infinity? That means we're getting an infinite number of rectangles, or at least we're approaching an infinite number of rectangles, and the width of each rectangle is getting smaller and smaller. So to answer this question, it's probably best just to talk through what we know about approximating areas and the whole integration process. So first of all, as n approaches infinity, the rectangles are getting thinner and thinner. And the thinner they get, the better the approximation. So therefore, as n approaches infinity, this expression, which is the the sum of the rectangles, it's just going to become a better and better approximation for the true area of the quadrant. And so when we do take this limit to infinity, it becomes the area of the quadrant. Now, what is the area of the quadrant? I mean, we might think, oh yeah, integrate, area under the curve, integrate. Good luck integrating the square root of 1 minus x squared. But we don't need to do that because we know how to figure out the area of a quadrant. It's just 1/4 of the area of a circle, pi r squared. And in this case, our radius is 1. 1 squared is 1, so we have 1/4 of pi, or pi on 4. And so therefore, as n approaches infinity, the area of all of our rectangles, right, approaches pi on 4. Or we could say the limit as n approaches infinity of an is pi on 4. And that's it. Now, back to our initial problem that we started off with in this video. I asked you to have a look at proving this inequality. And in order to do this, yes, it's an inequality, but in order to do this question, a really great method is to use areas, like we've just looked at. So, with that added bit of information, if you weren't able to prove this inequality at the start, have a go at it now with the skill set of proofs that involve areas. Good luck.